Hi, AP Calculus students. Welcome to video 4.5B. For this video, we don't have any more notes. All the notes that you need for section 4.5 were in the 4.5A video. But what you saw in the 4.5A examples video and on that assignment were the basic problems for substituting to solve integrals. So what you're going to see today is 4 examples for harder problems where you are using substitution to solve integrals. So we'll have 4 of these problems. Okay, so the first example that we see is, notice that this is a differential equation because we have the derivative of y with respect to x equals this expression. What they're asking us to do is solve this differential equation, meaning that we have to end up with a function with no derivatives when we're done, meaning that I have to integrate both sides. Okay, so the first thing we're going to do is, what I'd like to have is just a dy on the left. So when I integrate, the derivative and the integral cancel each other out. Plus, the variable of integration dx has to be with the x variables. So I'm going to multiply both sides by dx. And that will eliminate the dx on the left and put it on the right where it is properly supposed to be. There we go. So what I want you to know about this problem is that it is easier than it looks. This, when you see a problem, and you'll see 2 or 3 of them that have rational expressions in them and you're being asked to integrate, you very well could be like, oh my gosh, this is too complicated. When actually this is exactly what you need, and that's why it's there. Okay, so here's what I mean. When we integrate, notice we have this integrand has a product. I do see an inside function of 1 plus 1 over x. And so I'm wondering if my u, even though this looks complicated, do I just do the same thing I always do? And the answer is yes, you do. Your u, right, which I'm getting better at choosing, is 1 plus 1 over x. Or if you don't mind, I'm going to write this just as x to the negative 1 because I'm going to do my du. So I'm just hoping that I don't have to worry about it, that actually this is going to work out well. And it does, because notice when you take the derivative with respect to u, you get a 0 here. Here I'll bring the negative 1 out front and multiply it and reduce the exponent by 1. This is x to the negative 2, which is x squared. And let's not forget our dx. So notice what was actually very complicated is exactly what I needed. Okay, so let's go ahead. On the left, the integral and the derivative cancel, and I get y equals. On the right, let's do our u substitution and see if it is an expression we know how to integrate. Again, I always do my u first. Here's u to the 4th. There we go. And my the negative 1 over x squared dx is perfectly replaceable with the du. Look, this is actually a very simple problem. So don't let the rational expressions worry you. Okay, add 1 to the exponent, divide by the new exponent. I get y equals u to the 5th over 5 plus c. Also, you can multiply by 1/5, right? And now I can put my u back in. And I'm done, right? They started with x's. I needed x's to finish, and I'm done. Okay, let's start with, let's do a second one. Okay, for the second, let's see, number 2. Okay, now we're moving on to definite integrals, meaning it's a definite area, in this case from pi over 4 to pi over 2, and it's cosine of x over sine cubed x dx. Okay, now I'm going to need you to follow this pretty closely here, okay? There's a few things going on here. So this is our first definite interval, right? You could put this function into the calculator, get a look at it from pi over 4 to pi over 2 and see a definite area. And that's what they're asking us for here, okay? So there is an extra step in this problem that you have to pay close attention to, okay? First of all, notice that I do have a denominator, right? And so I think, again, students will tend to, what I'm about to write is wrong, but that's okay because you see a denominator, and my hint to you before was a lot of times we replace denominators with u's or inside functions. But notice when you go to do your du, you would have, by the chain rule, 3 sine of x squared, right? So you'd bring the 3 out front, multiply it, reduce the exponent by 1, and then multiply by the derivative of the inside function. Whoa. I do not have all of that, right? So students will sometimes tend to put too much or too little into their u, and it just takes practice, okay? So what if I made u just sine of x, right? It is inside the cubing function, right? And I do know how to integrate 1 over u cubed, so it's not like the cubed is a problem. So let's try again. Let's just make u sine of x. That makes du, okay, that's much nicer. Cosine of x dx. Okay, so don't be too worried. It just takes some practice. I see that exactly right here. Okay, so let's try the u substitution. I am not going to write pi over 4 and pi over 2, and you'll see why. Let me first make sure I have written an integrand that I know how to integrate, okay? So again, right here is my u cubed, right? I took care of that. And my cosine dx, I can totally replace with du. Again, your book will tend to put the du in the numerator. This is a 1 du, so I put the 1 in the numerator and the du next to it. Again, I do not want anything else with my integrand. Okay, this does look like something I know how to integrate, and here's what you need to know. It was easy for you to remember here that the x's needed to be replaced by u's. What I need you to know is this is a lower x and this is an upper x too. I can't keep those. I need to change those to u's. So what I do is whenever I have a definite interval, I make a little chart. Once I'm sure that I know how to integrate this u substitution, then I make a little chart to remind myself that this x of pi over 4 and this x of pi over 2 has to be u's also. Okay, a lot of students will forget that. Don't let that be u. Okay, so you may say, well, how do I get the u? You wrote a little function right here that switches x's to u's. It's right here, right? So we put in our pi over 4, sine of pi over 4 is the square root of 2 over 2, and we put our x in sine of pi over 2 is 1. These are my new u's. Be sure to match them up. Wow, because sometimes they'll flip upper and lower, right? So you have to be sure, right? One being bigger than the other. So here's what I mean. Pi over 4 is smaller than pi over 2. Square root of 2 over 2 is smaller than 1. Okay, so make sure you exactly what your pi over 4 is goes at the bottom. Your pi over 2 goes at the top. Is it possible later when you do a substitution that they flip values, which is bigger and smaller? Yes, it does, right? But you still write it exactly so it's matched up with your chart. Okay, everything now is switched to u's. Okay, so I'm going to integrate now. Okay, so if you don't mind, I'm going to write this as u to the negative 3. Right? Now I can add 1 to the exponent and divide by the new exponent. So the expression I have, this is 1, right? So a negative 1/2. This is u to the negative 2. right? So that's a positive 2 in the denominator. I am going to evaluate it from the square root of 2 over 2 to 1. I'm going to do my f of b minus f of a. Now, let's stop for a second. Could you, at this point, right when you integrated, could you replace your u with sine of x and then keep the same x's? Yes, you can. But I never do that. Why don't I do that? Because I'm on this path, I'm going to keep going. And not only that, but I did a u substitution because it makes the expression easier. Why would I go back right now with this expression, that was integrated, put in a sine of x, use pi over 4 and pi over 2? Will I be correct? Yes. But this is meant to be easier, so just keep going, okay? So f of b, when I put a 1 in here, that will be a negative 1/2. There's my f of b minus my f of a, okay? So this is the square root of 2 over 2 squared, which will be 2 over 4, right, when I square it, right, which will be 1/2, and 2 times 1/2 is 1. Negative 1 over 1 is 1. There we go. So let's check this again. Square root of 2 over 2 squared is 2/4, which is 1/2. 2 times 1/2 is 1. Negative 1 over 1 is a negative 1. Okay, but it was f of b minus of f of a, so that's a positive 1, and this is my final answer. Okay, let's try a third example. Okay, in number 3, let's do another definite integral. 1 to 3, 5x, 1 plus x squared dx. Okay, there's 2 things I want you to see in this problem. The first one is that you will have, like we did on section 4.5a, you will have an issue with a constant that you don't need, okay? That's gonna almost happen twice, and that's no problem. I just want you to know we know how to move constants in and out, okay? And again, we wanna practice the definite integral, okay? So I believe my u is 1 plus x squared because it's in the denominator and because it's an inside function. So let's see how this works for us. There's my u. That would make my du when I take the derivative 2x dx. Okay, I got the x, right? That works out well, right? Because this needs to be in the numerator. 2 issues here. I don't see a 2x. I see a 5x. So I don't want the 2. Again, I'm trying to make a perfect substitution. I have a perfect substitution here for u. I want a perfect substitution for du. I'd rather take care of it here than here. Okay, so the 2 needs to go. Okay, so when I replace this x dx here, right, I am going to replace it with a 1/2 du, right? So there's a couple things you can do. You can, right, I have a u squared, and here and here I have 1/2 du and a 5. I'll just write the 5 again, okay? But at the same time, I like it perfect, right? Perfect substitution here, 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 and here. Not happy about that 5 being there, right? I don't see it here, but I know what to do. I know that this expression that I have here is the same as this expression. I can move the constant to the outside. You don't have to. You'll get the right answer anyway. I just like the substitution of my expression of the integrand to be perfect. Okay, let's check it. Okay, now my 5's on the outside. Let's not forget it. I'm checking to make sure I've written a u substitution. I know how to integrate. I am not going to write my 1 and my 3. Those are x's. And if my u substitution is good, then I'll go, yes, let me replace those x's with u's also. So let's take a look. This is u squared in the denominator. And so I took care of this and this. The x dx, I'm going to replace with a 1/2 du. I'm going to put the 1/2 on the outside and the du where it belongs and a 1 in the numerator. I do know how to integrate this, so I am immediately not going to forget, again, that this is an x of 1 and an x of 3, and I need to switch those to u's also. Okay, again, here's the little math machine I made. It's the first thing I wrote that switches x's to u's. When I put in a 1, I get a 2 out. When I put in a 3, I get a 10 out. There, so 1 is now 2, 3 is now 10. Okay, let's go ahead now and integrate, okay? Again, if it's okay with you, 1 over u squared, I'm going to write as u to the -2. I'm going to add 1 to the exponent and divide by the new exponent. Okay, so the constants that I have right now, just coming on up over here, I have a 5/2 and it is negative, right? And this is u to the -1. I'm going to put that in the denominator. I am going to evaluate that from 2 to 10. Again, fully integrated. Could I put in 1 plus x squared here and evaluate it from 1 to 3? Yes, I could. This looks easier to me. That's why I wrote it. I'm going to keep going. So when you put in a 10 into the denominator here for f of b, that's -5 over 20, which is a -1/4, minus when you put in your a, right, then you have -5/4. Notice this becomes positive. And I have a positive 5/4 minus 1/4 is 4/4, which is 1. One more. What else could we do to you? The next one is hard for students. It is a pattern that you'll need to spot because they will do this problem to you once on the AP exam. This is called a double U substitution. And I don't mean W like the letter W. I mean, it is a double U substitution, meaning you're going to have to do 2 substitutions. Okay, so here we go. I just feel like I just put my good marker somewhere. Oh, well, we'll be fine. Okay, so let's integrate from 0 to 3 of x times the square root of x plus 1 dx. All right, here's my issue here. Usually what I'm looking for is an inside function. All right, u equals x plus 1. All right. And I'm looking for, when I take the derivative, when it's a power, right? We have power expressions here. When I take the derivative, I was always seeing that my u expression was being multiplied by a power that was 1 less, right? Because I was taking the derivative and it reduces the exponent by 1. I don't see that here. Like these are matching powers. So what do? We do what's called a double u substitution. So let's keep going. The derivative of u is 1 dx, right? Okay. So what happens here when I try to do a u substitution? Let's take a look. All right. I have the square root of u. So if you don't mind, I'm going to write that as u to the, rather than with the radical, right? I'm going to write that as u to the 1/2. My dx is du. All right, I'm good there. But take a look. I still have an x, right? I still have this x here. I can't have that, right? I can't have x's and u's. So what do? Here's what you do. Notice that when you look at this first expression that you wrote, u is equal to x plus 1. So what is x equal to then? Can I subtract a 1 from both sides? And isn't it true that u minus 1 is equal to x, right? So subtract a 1 from both sides. Well, okay, now I can replace that x with u's. Okay, so what I have going on is a double substitution. Okay, so now let's take a look. U to the 1/2, u to the 1/2, du. My x I now replaced with a u minus 1. This I know how to do with a little bit of work, right? So I'm going to remember that my 0 and my 3 are x's, and I need to switch those. So 0 and 3. So when I put a 0 in, that would make my u1. When I put my 3 in, that would make my u4. Okay, so I need to do a little bit of work here before I integrate. I'm going to distribute the u to the 1/2 to both terms. So this is u to the first times u to the 1/2 is u to the 3/2 minus u to the 1/2. Okay, let's integrate. I'm going to add 1 to the exponent and divide by the new exponent. I'm going to add 1 to the exponent and divide by the new exponent. There we go. So my integration will be 2/5 u to the 5/2 minus 2/3 u to the 3/2. And I am evaluating that from 1 to 4. Okay, excellent. Notice that I circled this minus sign right here because I'm going to have an f of b minus f of a for the 4, and then, right, minus, right, and I will have, I'll have an f of b is what I meant to say with the 4 here and here, minus, then I'll have an f of a with the 1 here and here. So I'll have a lot of minus signs. I have to be careful. Okay, I'm going to have to get kind of low here. Let's do f of b. Here we go. Let's put that 4 in. All right, so we have 2/5 times. When I put a 4 in here, the square root of 4 is 2. 2 to the 5th is 32. Right, still working on my f of b. I'm going to put a 4 in here. So I have 2/3. And when I put a 4 in here, the square root of 4 is 2. Cubed is 8. There. So there's my f of b minus. Now I'm going to do my f of a. This is a little nicer to put a 1 in, right? Because you just get 2/5 minus 2/3. There we go. So let's take a look here. I'm getting a little low. I would go over here, but I know the shine is a little strange for my living room there. Okay, so what I have is I have 64/5 here minus 16/3. I'm going to distribute the negative here, negative 2/5 plus 2/3. All right, I'm going to combine my like terms. Let's see, that will be 62/5 when I combine here and here. I am getting too low. We're just going to have to hope that the glare isn't too bad. 62/5 minus, this is a negative 16/3 plus 2/3, so that's a minus 14/3. Well, that's a pain in the butt, right? All right, wish I had a calculator in my hand. I'm going to have a, I'm going to make a common denominator of 15. Woo! Wish I'd eaten my lunch first. There we go. So when I multiply by 3, that's 6. 186. When I multiply by 5 here and here, that's 60. And I get, did I do that right? 3, that's 6. And I get 126 over 15. Oh, let's see, 0 carried the 2. Nope, this is a 70. Man, bad math. Let's see, 5 times 2. There we go. Yep, 70. There we go. 116 over 115. I was wondering because I knew the answer was 116 over 115 because obviously I tried it before I did this. And I'm like, uh-oh, I'm off by 10. There we go. So 4.5b was just showing you how to do some of the harder problems. They will have one of these on the AP exam. It just takes practice. Have a good day.